In the last few lectures, we have been looking at the solutions of the diffusion equation in terms of the concentration or the temperature fields. Solution equation, okay. Del square T is equal to 0 or del square C equal to 0 for the concentration field subject to boundary conditions. We had looked at solutions in a rectangular coordinate system, in a Cartesian coordinate system, in a spherical coordinate system using separation of variables, and another interpretation of the solution in a spherical coordinate system as the superposition of point sources and point sinks. I showed you that this interpretation has a one-to-one equivalence with the interpretation in terms of separation of variables. Okay. And we were, in the last lecture, we were looking at a distributed source. Okay. So, if I have a point source at a particular location x, I have a source at a location x of strength q, and my observation I am sorry, I should put the source as xs, source location, and x vector is the observation point. We had got the temperature field. Okay. So, basically this is a point source emitting heat q per unit time. Okay. And the equation for this, the conservation equation is del square T, okay, thermal conductivity plus Q delta of xs is equal to 0, and the temperature field was equal to 1, okay, Q by 4 pi k into x minus the source point. Okay. And the heat flux, we had got it as q into x minus xs divided by 4 pi k, 4 pi, there is no k here because we multiply by thermal conductivity to get the heat flux into x minus the source location whole cubed. Okay. If you had two sources, you just add up the contributions to each source. Each of those sources, the temperature field will be proportional to the distance of the observation point from that particular source. Okay. If you have a distributed source, if you have some distributed source, QV per unit volume, say due to phase change or reaction or some other such reason, and you have a location x, the equation that you have to solve is k del square T plus QV is equal to 0. Note that in this particular case, QV is the energy generated per unit volume per unit time, whereas Q in this case for a point source is the energy generated per unit time, and the delta function has dimensions of 1 over volume. Okay. So, in this particular case, the source could in general be a function of position. Okay. The solution for this equation is T is equal to integral dV prime. Integral is over the source points. Okay. So, this is the volume V prime. Okay. So, the integral is over the source points. Okay. QV at the location x prime by x minus x prime. Okay. This is the temperature at the location x. Okay. This is the temperature at the location x. Okay. and the heat flux at the location x is equal to integral dV prime qV of x prime into x minus x prime by x minus x prime the whole cube. Note that the observation point is x and the source point is x prime. So, these were the temperature fields that we had got for both a point source and from the point source. By considering a distributed source as a sum of a large number of point sources, we had got the temperature field for a distributed source as well. All of these were in an infinite domain. Okay. All of these were in an infinite domain. Okay. What happens if you have some source in a finite domain, for example? Okay. So, let us take the case of a source next to a boundary, okay. A source next to a boundary, okay, of source strength q next to a boundary, and let us assume that that boundary is perfectly conducting. Okay. If this is perfectly conducting boundary, that means that the temperature, okay, has to be equal to, it has to be a constant along that boundary, because if it is perfectly conducting, heat is conducted instantaneously and temperature equalizes instantaneously. Okay. If it is perfectly conducting, then there is no, since the temperature is a constant, okay, is a constant independent of position on that boundary, okay, there cannot be any heat flux tangential to the boundary, because a heat flux tangential to the boundary, okay, requires a temperature gradient parallel to the boundary. Okay. A heat flux in the tangential direction requires a temperature gradient along the boundary. Okay. So, if I take the cross stream the vertical coordinate perpendicular coordinate as z and the coordinate along the boundary as x, if the boundary is perfectly conducting, there can be no heat flux parallel to the surface, because if it is perfectly conducting, the temperature is a constant along that boundary. If the temperature is a constant along the boundary, there is no heat flux along the boundary. Okay. Therefore, the flux lines necessarily have to be perpendicular to the boundary. Okay. So, the flux lines, for example, the flux lines necessarily have to be perpendicular to the boundary. Okay. Okay. At the boundary itself, they have to be perpendicular to the boundary, because the flux cannot have a component that is parallel to the boundary if it is a perfectly conducting surface. Okay. And let us assume that the distance between the source and the surface is L. Okay. Let us assume that the distance between the source and the surface is L. Okay. How do we find the temperature field in this case? Okay. We can no longer use the simple, okay, relationship Q is T is equal to Q by 4 pi k into x minus xs. Okay. This expression can no longer be used, because there is a boundary. This just gives a radially outward heat flux. Okay. This just gives you a heat flux that is radially outwards. Okay. Okay. Radially symmetric. This heat flux and this temperature variation does not satisfy the condition that the surface is perfectly conducting, and therefore, the temperature has to be a constant on that surface. Okay. This does not satisfy that condition. Okay. Okay. So, how can we satisfy this condition in this particular case? Okay. You can do that using what is called the method of images. Okay. For the physical configuration that we have, the physically relevant domain is for z greater than 0, okay, for z greater than 0 is the physically relevant domain. Okay. We can replace this by a configuration consisting of a source at a distance L, okay, and a sink below of equal strength at another distance L. Okay. Okay, above and below the physical boundary. Okay. Okay. So, both of these are located in, you are replacing a physical boundary with a source near it by no boundary, but a source and a sink. Okay. Placed symmetrically about the location where the boundary is in the physical domain. Okay. And you can see that in this configuration, just by symmetry, right, the flux lines have to come out of the source and they have to go into the sink. Okay. And they have to go into the sink. Okay. So, the flux lines have to come out of the source and they have to go into the sink. Okay. Since the source and sink are separated by a distance 2L, okay, at the bisecting plane L, okay, at the bisecting plane L, right, okay, because it is symmetric, there is a source and a sink that is symmetric. At the bisecting plane L itself, right, the heat flux lines have to be perpendicular to the surface, because the configuration is symmetric. Okay. Because the configuration is symmetric. Therefore, the heat flux lines have to be perpendicular to the surface at this location. So, the physical problem, which consisted of a source next to a perfectly conducting wall, the physical problem of a source placed next to a perfectly conducting wall, has been replaced by a problem where there is no wall, but there is a source at a distance L above where the wall should have been, and a sink at a distance L below. Okay. So, this one is plus Q and this one is minus Q. Okay. The sink at minus Q is what is called the image. Okay. Okay. So, if this is the source location x source, this is the location of the image. Okay. X image. Okay. So, source is a distance, perpendicular distance L above, the image is a perpendicular distance L below. For this configuration, the temperature field for z greater than 0, the temperature field in the domain z greater than 0 is identical to the temperature field for our physical problem, which consists of a conducting wall, perfectly conducting wall at the boundary. Okay. It is identical to that. Okay. And for this configuration, the configuration with the source and image, I can get the temperature field quite easily. Okay. T is equal to Q by 4 pi k into 1 by x minus the source location minus 1 over x minus the image location. Okay. So, that is the temperature field. The temperature field in the domain z greater than 0 is the same as the temperature field I have in my physical problem over here. Okay. It is the same as the temperature field that I have in my physical problem here. Okay. Therefore, this shows that you can get the temperature field for this configuration by just writing this as the superposition of a source and an image in such a way that at the symmetry plane between the source and image, right, the heat flux lines are perpendicular to the surface. If the source is plus Q, the image has to be minus Q in such a way that the heat flux lines are perpendicular to the surface. Okay. Okay. So, this temperature field, this is what is called the Green's function for what is called the the constant temperature condition. Okay. Since I have a constant temperature on the surface, perfectly conducting, that means that the temperature equalizes instantaneously across the entire wall, constant temperature condition. Okay. So, this okay. Now, I can do a similar thing for a distributed source. Okay. So, for a distributed source, okay, if I have some source here, okay, QV of x, okay, and perfectly conducting, I can replace it by an image of the distributed source. Okay. Okay. By an image of the distributed source. Okay. So, let me try to draw the image a little bit better. Okay. These are exactly of the same shape, they are mirror images of each other. Okay. They are mirror images of each other. So, if I have a source here, okay, and I have an observation point here x, x vector, then there is an image of that source at this point. Okay. Therefore, the temperature field can be expressed as, okay, if it was just one source, right, in an infinite medium, the temperature field would be equal to integral dV prime of QV of x prime by, okay, x minus x prime into 4 pi k. Okay. In this case, since I have an image as well, the temperature field it becomes integral dV QV of x prime into by 4 pi k into 1 by x minus x prime minus 1 over x minus the image, okay, minus 1 over x times the image. So, x minus x prime is this distance, image is this distance. Okay. So, basically I have to put an image at which is symmetric with respect to source, whose perpendicular distance from the plane is the same as the perpendicular distance of the source from the plane. Okay. The perpendicular distance of the image from the plane has to be the same as the perpendicular distance of the source from the plane. Okay. So, therefore, I have to put in this image, okay, of the source, okay, and this will give me the temperature field that satisfies the boundary condition that the temperature has to be a constant on the surface, or that the flux lines have to be perpendicular to the surface for this particular configuration. Okay. So, this thing is what is called a Green's function. Okay. This is what is called a Green's function. Okay. Which satisfies the constant temperature condition at the surface, which satisfies the constant temperature at the surface. It goes by the name of the Dirichlet Green's function. Okay. G of x minus x prime is equal to 1 by x minus x prime minus 1 over x minus the x image prime. Okay. Note that this was the equivalent Green's function, okay, and I should have a 1 over 4 pi k here. So, let me just write that factor 1 by 4 pi k here, okay. G of x minus x prime, it is called the Dirichlet Green's function, is equal to 1 over 4 pi k 1 by x minus x prime minus 1 over x minus x image prime. Okay. So, knowing what is the location of the source x prime. So, typically if x prime is equal to x prime, okay. Okay. If I have a coordinate system which is 0, okay. So, let us say I have a coordinate system which is 0, z is equal to 0 on the plane and the plane is in the x y direction. Okay. Then if x vector is equal to, or rather x prime is equal to x prime, y prime, z prime, then the image is equal to x prime, y prime minus z prime. Okay. It is a reflection of the source on this plane at z is equal to 0. Okay. For the infinite medium, this was the Green's function 1 over 4 pi k into x minus x prime. By changing that function to include the effect of the image, you can satisfy the boundary condition at the surface, that is the boundary condition at a perfectly conducting surface. Okay. And the Green's function for that is called the Dirichlet-Green's function. Okay. What if you had a perfectly insulating surface? Okay, what if you had a perfectly insulating surface? Okay. For an insulating surface, let us say this was insulating, this is the z axis, this is the x axis. If I have a source here at the location x source, right. For a perfectly insulating surface, there can be no heat flux going through the surface. For a perfectly insulating surface, there can be no heat flux going through the surface. Component of the heat flux perpendicular to the surface has to be 0 because the surface is insulating. Therefore, you can only have flux lines going parallel to the surface. Okay. So, you can have flux lines only going parallel to the surface. And obviously, the temperature field due to a point source does not satisfy this condition, because the temperature field due to the point source is radially symmetric. Okay. It is spherically symmetric, whereas this one is not spherically symmetric. Okay. So, how do we satisfy the boundary condition? We can do it in a manner similar to what we did for the previous case. Okay. There is no physical boundary. Okay. So, if L was the distance of the source from the boundary, okay, then we have, in this case, we have a source x s, okay, at a distance L from the surface, okay, and we put another source. The image is also another source of plus q, okay, of the same plus q. Okay. And if you have this configuration, you can easily see that since the heat flux lines are outward from each source, okay, they are outward from each source, at the plane of symmetry, the heat flux lines have to go parallel to the surface. Okay, the heat flux lines have to go parallel to the surface. Okay. And this basically satisfies the boundary condition at the surface. The fact that there is no net flux at the surface is satisfied by putting a source at a location at a distance L below the surface. Okay. So, for a perfectly conducting surface, you put a sink, and for a perfectly insulating surface, you put a source at a distance L below the surface. Okay. And the temperature field due to this T of x is equal to Q by 4 pi k into 1 by x minus the source point plus 1 by x minus the image point. Okay. So, you have to add up the contributions due to the source and due to the image for an insulating surface. Similar thing applies for a distributed source that is close to the surface. Okay. So, if I have, for example, a distributed source close to an insulating surface, okay, which is bounded by an insulating surface, okay, you can replace that by removing the surface and putting an image below. Okay. This is z, this is z, and this is x, by putting an image below, okay, this. Okay. Both of these are sources, okay. Both of these are sources of equal source strength, okay. And the image point, of course, okay, if you have a source xs x prime is equal to x prime y prime z prime, then this image location will be equal to x prime y prime minus z prime. Okay. So, that is the image location. Okay. And the temperature field due to this T of x is equal to integral dV prime q of x prime by 4 pi k into 1 by x minus x prime plus 1 by x minus x I prime, okay, where x prime and x I prime are related by this relation. Okay. This can also be written as integral dV q of x prime by 4 pi k into g of x minus x prime, okay, where the Green's function for this, okay, for zero flux condition, okay, it is called the Newman Green's function. G n is equal to 1 by 4 pi k. I am sorry, in this formula I should not have 4 pi k here. Okay. Okay. The 4 pi k comes into the definition of the Green's function. Plus okay. Basically, for zero flux boundary condition, you are superposing two sources, so that the heat flux is parallel to the surface at the insulating surface. Whereas, for constant temperature boundary conditions, you are superposing one source and a sink, so that the heat flux is perpendicular to the surface. There is no contribution of the heat flux parallel to the surface. Okay. So, with this I will conclude our discussion of solution of the diffusion equation. Okay. We started off by solving the diffusion equation or the diffusion equation with an inhomogeneous term in different configurations. Rectangular geometries for the heat conduction in a block, a rectangular pipe, spherical geometries, point source, point dipole, superposition, okay, and then distributed source, and then how to apply boundary condition. Okay. So, with this we will close our discussion on the diffusion equation. In the next lecture I will consider flows where convection is dominant, okay, flows where convection is dominant. We will see how we can solve problems of dominant convection. That I will start in the next lecture. I will see you then.